This video is going to look at universal gravitation. Now we have already looked at gravity on a small scale, and small here being, we are within a couple hundred meters of the surface of the Earth. The big thing that we've got with this, if this is the Earth has a radius of about 6 million meters, 6.5 million meters. So when we are looking at something as big as the Earth, 6.4 times 10 to the 6th meters, that's really big. When we are, when we add a couple hundred meters to that, it's not really a noticeable difference. If we add 1,000 meters to this, right, 6.4 times 10 to the 6th meters, or 6,400,000 meters. If we add 1,000 to this, we are still not really changing this number very much. So anytime we are near the surface of the Earth, within even a few kilometers, we're not going to notice a difference in gravity. But universal gravitation is saying more. We've got that, and then we've got maybe the moon out here, and this is an actual noticeable difference in gravity away. Right? When we put the moon out here and we say here is a distance from the Earth to the moon of 384 times 10 to the 6th meters, now we are definitely looking at something considerably different. So we're going to look at universal gravitation as being the gravitational force in general that one object exerts on another. If we're going to want to do this same problem with the Earth and the moon, I'm going to just jot down a couple of these values right now. The mass of the Earth is about 6 times 10 to the 24th kilograms. And the mass of the moon is about 7.3 times 10 to the 22nd kilograms. Universal gravitation is something that exists between any two objects that have mass. We get a formula first. And we need this letter G. It's a capital G, and it's a constant. It's about 6.67 times 10 to the negative 11th. The whole thing has to come out to newtons, so this is going to be newtons times meters squared divided by kilogram squared. And it's just a constant. It's the gravitational constant. I've got two m's in this equation. The first one can be the mass of one item, one object, and the second one's just the mass of another. To get this force, we need two objects. Each object has to have mass. Not a big deal there. R is the separation distance. Not a big deal because pretty much everything that we work with has mass. I use a capital M and a lowercase m. Sometimes you'll see the same formula with a G, mass 1, mass 2, over R squared. I like to use a capital M and a lowercase m. They're being multiplied together, so it doesn't matter which is which, but I tend to use a capital M for the larger of the two bodies, and a lowercase m for kind of the mass that's experiencing that force. Newton's third law says they're both experiencing the force, right? That whatever force the Earth is exerting on the moon is exerting the same force back. But if I'm doing a problem where I'm saying, like, I want to find some information about the moon. I want to find the force on the moon. I want to find the acceleration of the moon as it moves around, or the orbital speed or something like that. Then for me, I will call this my lowercase m and say it's due to this big M. That's kind of the overall idea of the formula. And we have a handful of different things that we can do with this. We can look at a moon orbiting around a planet. We can look at a very, very different case. It's not really different. Of a planet orbiting around a star. So orbits, those are fine. Or if we have a planet, we might do a satellite orbiting around a planet. That's fine, but again, another orbit. We could have a planet and we are going to launch a rocket. So that it moves off the surface of the planet out to far away from the planet. That would make a lot of sense. So orbits are good for this. Rocket launch, that's good for this. Or problems in space where there aren't, big gravitational fields that we're worried about, like right near the Earth. Maybe I've got a person in space and let's even say another person in space. These two are going to attract each other. We might also have, two objects in space that could matter. We might also have, here is like one planet, another planet, and we've got a spaceship that's traveling from one planet to the other. That kind of a situation. These are all, interplanetary travel. These are all situations where we might use this larger scale gravity. I will give you some examples of how to actually do problems with this. For right now, this is the idea.